welcome to this second industrial session. We are glad to be the second one after the transport yesterday. So this afternoon we will focus on industrial system that doesn't move, that stay at the same place. So we have a nice panel today. They will present themselves in details, but we have people from oil and gas, people from manufacturer of burner for oil and gas and for the cement industry, and also people involved in boilers in power production, and myself that plays with steel and glass industry. And we are also here on behalf of the IFRF, and our General Secretary, Mohamed, will give a few words of presentation of our technical foundation. So, just to present one of the speakers, so myself, I am now combustion chief expert at Fifstin that make furnace and lines for the steel industry. Before that, I was assistant professor a few years. And I am also a member of the IFRF. I am vice president of this foundation. And so we organize technical meeting and so on. You will have some details. And also I participate in the organizing committee of the INFUB, that is a smaller conference than here today, but that is very focused on furnace and boiler, and also very interesting from an industrial point of view. Just in short, why are we here? Why are we invited? Because in the different sector we represent, we use a lot of fossil fuels. And so we present a big part of the industrial emission. For example, here I just highlight the steel sector where I work. And we are responsible for almost 8% of the global greenhouse emission. So it's not a small percentage, it's a huge percentage. And so we need to make efforts to reduce these emissions. So of course I will not go in details, maybe in the question and answer after that, if you have some question, but just to give some figures, here is the steel production during the past years. And you can see after the year 2000, the steel production in the world have almost doubled. And this is mainly due to China that invested a lot in steel production. And so the link with combustion is coal, because coal is used in a big part of the process to extract the iron from the iron ore. And this consumption of coal is almost the same as the consumption as the quantity of steel we produce. So it's almost 1.1 gigatons of coal that is consumed every year. So you can do the math if you want, but if you see 2 gigatons of coal that is burned, it's a huge quantity of CO2 that is released in the atmosphere. And here is a quick summary. Again, I will not go in detail now, but we can ask questions later if you need. And if you look at I don't have a pointer, but in the upper left, you see where the coal plays a role to be mixed with the iron ore to produce the steel. This is the main road today to produce steel. Almost 80% of the steel is produced this way. And this is where the efforts are to be put now to reduce the CO2 emission by using other methods of extracting the iron. And the way is called DRI, and for the moment this way is only 5% of the total production, and this needs to be increased. The problem about that is that there are technical solutions, but it needs a lot of quantity of electricity if we want to use hydrogen to create the hydrogen. So we need a nuclear reactor near to the place where we produce the steel. This is possible from a technical point of view, but as you can imagine, it's huge investments. So, and the lifetime of the steel production units, it's very long. It's 10 of years. And on the right side, you have some idea of, I'm sorry, it's a little bit small in the screen, but it's all the steel producers in the world and the average age of the plants. And since the lifetime can be tens of years, if the plant have 10 or 15 years, we will have to wait 10 or 20 more years so the investment are possible. Otherwise, the plan is too new to make some major changes. It will be absolutely too expensive. So this is in short. Here is an example of what we make in our company. We are not the only one. Just to show where the energy is used. Most of the energy is in the steel production, but also 30% is in the part where you, after you make the steel, you must transform it to make it usable to make a car, chairs, whatever you want. And this also is 30% of the energy that is used, and also everybody is working on how to reduce this CO2 emission from this area of the steel production. One optimistic thing on this, I know we are not reducing at a very fast rate the CO2 emission in the industry, but here is just an example of where emission systems are put in place to try to control CO2 emission. And as you can see, more than 20% of the industrial emissions in the world now are concerned by this scheme of exchange. It means that the effort is starting to have an effect, and especially on the price of the CO2 emitted. For example, this is the price in Europe, and you can see that there is a huge increase in the price of CO2 emitted. So this is an important point to push to lower the emission. So that's all for me. And I will give the floor to Mohamed Pourkashanian, that is that you work in Sheffield. And I think, Mohamed, you will present yourself. So Mohamed is not here. Is he connected by Zoom today? Yes, and you are here.
Thank you, Sébastien. And good afternoon from the UK. What I will try to do in the next 15 minutes to set the scene why we think industrial decarbonization is very important, and what are the challenges and what are the opportunities in terms of research and technology innovation. Next slide, please. So, in terms of the industrial decarbonization, the challenges and the opportunities that are available, first of all, let's look at it why we believe it is important to decarbonize industry. If we want to reach the net zero target by year 2050, that will require extensive systematic changes across all sectors, including industry. And what we mean by industry is really energy-intensive industry, such as metals and minerals, chemicals, ceramic, glass, oil refineries, and not also excluding less energy-intensive manufacturing. However, in order to implement the industrial decarbonization strategy, we do have not only technical challenges, but we also have to deal with legal and financial challenges that are attached to the industrial decarbonization. And in order to resolve some of these issues, significant fundamental research, what I mean by fundamental research, TRL 1 to 3, and the demonstration, pilot scale demonstration at a TRL level 3 to 6 is required. Next slide, please. So, if we look at the very recent data from IEA, this is the Tracking Industry 2021 data, you clearly see the reason that Sébastien just talked about, that why industrial decarbonization is important. Just looking at the number for data for 2020, you see that global emission from industry was around 8.7 gigaton of CO2. That's around 26% of the global emission. Even that you take into account that there was a reduction in 2020 of 1.6% due to the COVID-19. Now, if we want to reach the zero target or net zero target by 2050, we have to reduce this CO2 emission at a global level to under 6.9 gigaton by year 2030. And that is a big challenge for researchers and for industry to make sure that we find the technology pathway to deliver that. Next slide, please. So where the industrial decarbonization comes from? Of course, we have, we need fuel for the production of the feedstock and required for the manufacturing product. We need heat, fuel for heat and cooling. We also need fuel for process heating and cooling system, as well as powering the machineries. Now, the technology pathway to industrial decarbonization is clearly defined in a number of important pathways. This includes, as you may heard a lot about it and done research on it, carbon capture, utilization and storage, industrial electrification, and I mentioned in a cautionary note, if possible, energy efficiency improvement and optimization, and switching to a low carbon fuels such as hydrogen and even hydrogen carrier fuels like ammonia. Next slide, please. Now, what are these industrial decarbonization technology pathways? Well, if you look at the energy efficiency, I believe it is the most cost-effective option in near term. With the lowest cost, you can reduce you can reduce the CO2 emission. And by simple technology like installing or improving heat recovery system, utilizing waste heat, especially low temperature waste heat, and also upgrading the processes and equipment. In addition to that, we also can look at the strategic energy management in terms of system level, which also will improve energy efficiency. Carbon capture and utilization and storage, of course, the technology that available now, part of it, but is expensive technology. Existing technology that can be implemented include oxy-fuel, pre or post-combustion CO2 capture using different solvents. However, where the research is needed and where we can improve the or implement carbon capture as a part of future technology, we do need to do research in areas such as rotating packed bed, where it reduces the size of the CO2 capture plant, or MCFC, molten carbonated fuel cell, where it produces electricity, captures CO2, and brings in that optionality and flexibility to the process by making hydrogen if it's required. And also working on the materials for CO2, different solvents, and more stable solvents to reduce the cost. And also in the utilization in new market, how to make that capture CO2 more valuable. For example, by converting it to the sustainable aviation fuels or high value chemicals. Next, another technology that can be used in industry by fuel switching to biomass, but capturing the CO2, either utilizing it or storage, but at the same time, not only reduce the CO2, but go negative because of using biomass. Next slide. And continuing with that technology pathway, fuel switching from the fossil fuel, such as coal or liquid fuels or natural gas, to low carbon fuels, such as electricity, if it's produced from renewable sources, or biomass, hydrogen or ammonia. So in this sort of area, developments of the fuel flexible processes and energy system is important. How flexible is that energy system that can use different fuels? The availability of the biofuels or biomass, and how to integrate these new systems with different technologies. Now, as I mentioned before, industrial electrification is also important, and this is providing electricity is produced from from renewable sources such as wind or even nuclear, but is not applicable to every technology that needs to, or every industrial processes that needs to be decarbonized. And finally, hydrogen, which is at this moment a lot of interest on hydrogen to be used for industrial decarbonization. But two key points: if you want to have a green hydrogen or low carbon hydrogen, the cost of hydrogen at this moment is very high, and also availability is an issue. And I show you the reason for it. Next, please. Next slide, please. Yes. Now, if you look at demand for hydrogen, you can see that at every sector, there is a requirement for hydrogen if they want to decarbonize. Whether you're using it as a decarbonizing heavy industry or transport or heat for commercial use or domestic use, all requires hydrogen. And that hydrogen can only come from the renewable sources or nuclear energy, or green or blue hydrogen from natural gas. However, that option, at least in UK and in Europe, is under question because of the security of natural gas supply and high cost of hydrogen. So based on that sort of reasoning behind the industrial decarbonization, let's look at what IEA Net Zero 2050 states. Next slide. Next slide, please. Yes. The key pillars that has been identified in IEA Net Zero 2050, there are 7 key pillars that are very important in order for us to reach the net zero target. And number 5 in these key pillars are the hydrogen and zero carbon fuels. And if you look at that prediction, as reported by IEA, you will see that industry, different sectors within the industry like refineries, iron and steel, chemicals, all these sort of different energy intensive industry, by year 2050, they will use plenty of hydrogen, green hydrogen or blue hydrogen, if available, in order to contribute to that net zero target. And these numbers clearly shows that at this moment, for example, the refineries use some, but chemicals, again, and other uses, but you see that the use of these fuels in other sectors in industry significantly increases over the next 30 years. Next slide, please. Of course, having Combustion Symposium and our research colleagues, they know that hydrogen was one of the first fuels that was looked at. And especially if you look at the first Combustion Symposium preceding, you will see that a lot of hydrogen research has been reported. At the time that, for example, I was starting my PhD, I used to look at the papers that Professor Graham Dixon Lewis and Professor Alan Williams did in 1960s on hydrogen. So hydrogen combustion has been looked at in great detail, especially by the researchers from Combustion Symposium. It has certain properties that are beneficial to the combustion process, and there are some disadvantages also associated with it. Next slide, please. One projects that we have been working on in UK, funded by the UK government, is looking at how to decarbonize, for example, industrial sector, using biofuels and comparing that to the hydrogen. Some of these data will be published very soon, but if you look at these data, you clearly see that for hydrogen, before industry invests significantly on it, there are some fundamental challenges needed to be identified and resolved, solution to be found for them. And on the biofuel, this fuel that was produced from waste also is limited on the availability, but potentially economically attractive for direct replacement of the fossil fuel. And finally, just to look at, next slide, to look at this is not next, yes. You see that I looked at all these hydrogen value chain and identified where the research are needed in terms of production, in terms of transport, and in terms of end use. This is where we are involved, for example, on use of hydrogen, on aviation. A lot of research challenges there, in rail, in use of ammonia, in, for example, in marine, use of hydrogen for steel industry, or glass industry is a high area of require significant research, or even blending of hydrogen with methane requires significant research. So just next one. And there are a lot of international collaboration that you
Mohamed, you have 1 minute left, please.
Yeah, sure.
Thank you.
And I would recommend you to have a look at the CEM. And next one, please, my concluding remark. So, foundation to deliver net zero for industry. What is important? Carbon pricing, not only at the national level, but at international level. Market regulation, decarbonization, standards for the development and investment flow, and making that culture change for getting consumer to choose low carbon products, or getting investors to choose low carbon for investing. In terms of transforming industrial processes, accelerating innovation of low carbon technology is important. Adopting low carbon technologies for building infrastructure is important, and improving efficiency. And finally, research and technology innovation in terms of low zero carbon fuels, combustion performance, emissions, flame characterization, burner development, energy materials, especially for hydrogen, smart control system, and cost reduction. Technology is also important, and we should also not forget, whatever we do, we need to look at life cycle analysis. The next slide is mainly for flame foundation, but let's go through two of them together. Next, please. Next one. And just to remind you that IFRF will have special session on hydrogen combustion in October, and we will welcome you all to that meeting. Thank you, Sébastien.
Thank you, Mohamed. And I forgot to mention that Mohamed is the General Secretary of the IFRF. And now I would give the floor to Claude, that you will introduce yourself.
Thank you. Good afternoon, everyone. I am Claude Prébendé. I have more than 30 years of experience in combustion in different domains and with many fuels. I've been working in Total Energies for 16 years, and I was lucky to be involved in an ambitious project, CO2 CCS pilot in the southwest of France in 2010, with the CO2 capture by oxy combustion in an existing 30 megawatt boiler, and transportation, injection and storage in depleted gas reservoir. We injected 50,000 tons of CO2. Today I am in charge of fired equipment, specification and mechanical design in our oil and gas facilities, offshore and onshore, refineries, petrochemicals, and power plants. More and more, I am involved in an R&D program to reduce CO2 emissions. Total Energies is a major international oil and gas company and exists since 1924, almost 100 years. My company is undergoing a profound change. Last year, Total became Total Energies, a new name for a new ambition to become a major player in energetic transition and to achieve net carbon neutrality by 2050, together with society. Historically, Total Energies continues to produce oil and gas, mainly liquid natural gas. And for 16 years, Total Energies is involved in solar energies by developing a new generation of photovoltaic panels, and more recently, wind energy, mainly in offshore. The purpose of my presentation is focused on the solutions to be the solution we are implementing progressively in our facilities to decarbonize our operations. In the past and today, the CO2 emissions come from gas turbines, boilers, furnaces, and other fired equipment, and flaring. We measure ourselves the methane emissions in our flare flames with a drone. In fact, there is insufficient air inlet in the flame to properly burn it, to burn all the flare gas, sorry. And you know that methane is more than 25 times as potent as carbon dioxide at trapping it in the atmosphere. There are two paths to reduce GHG emissions. Either we'll reduce or replace hydrocarbon fuel gas, or we capture emitted CO2. The first solution is the recovery. It's better to valorize the recovered flare gas instead of burning it. And we recover the heat from the hot exhaust gas from gas turbine to produce steam, and this steam for the steam turbine to produce high efficiency electricity. The maturity of the technology is very high. The second solution is electrification. As I told before, Total is produce renewable energy by solar and wind energy. On the right, you see an electric boiler which could replace a gas firing boiler, but there are two challenges to implement this technology. To install high voltage electrical supply and to control the water quality, mainly the conductivity of water, because this technology is based with the electrodes. Another solution is to use decarbonized fuels. You recognize on the left the friendly color of hydrogen. Green hydrogen is produced by electrolysis of water with renewable electricity. And blue hydrogen is produced by steam methane reforming plus CO2 capture. And the strategy of Total Energy is to use the hydrogen and ammonia mainly in the gas turbine, because we have 200 gas turbines in our fields. And it's very difficult to control the CO2 emissions. And this way to use hydrogen and ammonia is a good way. The challenge is to control the NOx emission, the stability, the thermoacoustics, etc. There are many conferences yesterday about this topic. And there are simulation modeling and testing program ongoing with laboratories. The last solution is the carbon capture, storage, and use. This solution is very attractive comparing the post-combustion CO2 capture by a chemical solvent absorption. The challenge with this solution is to produce oxygen at high capacity and high purity with the lowest electrical consumptions. For example, with the cryogenic distillation of air. When we use oxygen for the combustion, oxy-combustion, we implement a specific oxy burner to be developed. And there is, to maintain the temperature around the tubes, the water tubes inside the boiler, there is a flue gas recycle to be implemented to dilute the high temperature from the flame of the oxy burners. At the exhaust of the boiler, we have water, CO2, and an excess of oxygen to optimize the combustion. And with a very light water removal, we can capture the CO2. And after, there are two main ways, two main paths. Either the geological storage, as we demonstrated this solution in our pilot in 2010. It's a permanent sequestration. The other way is to use this CO2 at different purity for food, for drink, or the chemical ways like e-fuels and methanol, for example. In conclusion, I would say that Total Energy encourages all researchers around the world to develop these emerging technologies as efficiently as possible and as quickly as possible, to integrate them in our facilities or to our partner and customers' facilities, because we are committed to respecting carbon neutral by 2050. Thank you for your attention.
Thank you, Claude. We will switch to the next speaker that is online, unfortunately, or fortunately is connected. So, Chuck, the floor is yours.
Good afternoon, everyone. I'm disappointed I'm not there with you in person. I found out on Friday evening that I have COVID. The good news is that the symptoms are basically gone now, but I'm missing the pleasure of being with you in person. I've been working in industrial combustion for about 40 years. I've been working at John Zink Hamworthy Combustion since 1998. And one of the things that surprised me in the last couple of years is the intense interest in particular in hydrogen combustion. John Zink has been doing hydrogen combustion for many, many years. In ethylene cracking, it is the dominant fuel, typically has 80% or more hydrogen in it. It's a waste product, so it makes economic sense to use it. But as Professor Pourkashanian pointed out, the cost of hydrogen today is very expensive compared to fossil fuels, which means that in general, our customers normally wouldn't be that interested in something like that until the cost came down or until regulations changed to force them to use it. But they're being very proactive, which is not something that I'm used to seeing, but it is a nice change. Next slide, please. John Zink provides equipment to the refining, the petrochemical, chemical, power generation industries, and Total Energies is one of our customers. So we're coming at it from the perspective of how do we burn various fuels. And as you know, lots of interest in using hydrogen for combustion, predominantly because it doesn't make any CO2. It also doesn't make any carbon monoxide or smoke. And according to IEA, it's an important piece in the Zero Emissions 2050 puzzle. In the United States recently, an infrastructure bill was just passed where they want to establish at least 4 hydrogen hubs. Next slide, please. I live in the state of Oklahoma, and we are looking at partnering with a couple of neighboring states to form a hydrogen hub. For our test facility, we get our hydrogen from Louisiana, and that's about a 12-hour drive by tanker truck. So we don't have any hydrogen production at the moment in the state of Oklahoma, any large-scale production, and that may change with this hydrogen hub. Next slide, please. They're looking at establishing hubs not only in the United States, but also in Canada. The map on the right shows a bunch of them that are in the planning phase now. So great interest in forming these hydrogen hubs. Next slide, please. In Japan, Mitsubishi is establishing a park dedicated to hydrogen combustion, particularly with power generation. Next slide, please. A bunch of headlines that have appeared in the news just this year. You can see in the top right, Amazon, they're talking about investing, if I remember right, $4 billion in green hydrogen companies. Spain's introducing one. There's a new program for the AICHE. ExxonMobil's talking about it. So lots of interest there. By coincidence, this morning, there were 2 things that appeared in the news that were new, at least to me. One of them is the Nuclear Hydrogen Initiative, where 40 participants are getting together around the world to look at using nuclear energy to produce hydrogen. And the second one is a company called EPRO Advanced Technology has developed a powder that's predominantly silicon. And so in a powder form, you can take this chemical, drop it into water, and it generates hydrogen. And if that is successful and cost effective, that would be a major advancement because, as you know, one of the challenges with using large-scale hydrogen is transportation. So if you could use a solid powder, that would really give a lot more flexibility. Next slide, please. They're talking about a blue hydrogen plant. Advance one more, please. And here's a schematic of it. So this would be the largest blue hydrogen plant in the United States. Air Products is talking about investing, if I remember correctly, about $4.5 billion in this new plant. And they would be injecting the CO2 into some existing wells for oil and gas. Next slide, please. And the U.S. Department of Energy has a very big program looking at all aspects of hydrogen, its production, its distribution, its usage in a variety of industries. So lots of interest, lots of research being done in this area because of the potential of eliminating CO2 depending upon how you make the hydrogen. Next slide, please. And then this came from the IFRF earlier this month, where they are talking about Shell building a 200 megawatt renewable hydrogen plant in the Netherlands. So this would be a green hydrogen plant because it would be electrolyzing water with renewable energy. Next slide, please. So you've heard a little bit already about different colors of hydrogen. Of course, hydrogen doesn't have a color itself, but when we talk about how it's made, it depends on what is the source of the hydrogen and what's the energy used to make it. And you've heard about blue and green hydrogen. If you were to make hydrogen with electricity from nuclear power, that would be considered red. Some folks call that pink. So a variety of ways we talk about that. And of course, the holy grail is to make it with renewable energy, such as wind, hydro, and solar. And next, please. Currently, 95% of the hydrogen that's made in the world is by steam methane reforming, and that unfortunately generates lots of CO2. So it's very cost effective, but it's not very environmentally friendly. So this is what's being targeted, especially using electrolysis with electricity made by something other than a fossil fuel. Next slide, please. So you at the symposium are very well aware of the differences between methane and hydrogen. We have a lot of experience burning hydrogen, but it is a different fuel. So if customers think that they can simply change a valve and switch from one to the other without making any changes, that's probably not going to happen. The changes, generally speaking, are not major, but nonetheless, they do need to be taken into account. On the good side, hydrogen is very easy to burn. From a combustion engineer's perspective, we don't have to be very accurate with our mixing, but on the negative side, it's a small molecule, it has a high diffusivity, it leaks very easily, it has a very wide flammable range, so it's easy to ignite, and therefore the transportation and storage is clearly an issue for that. Next slide, please. So clearly the main advantages are no CO and CO2. Depends on how we make the hydrogen, of course. If we use steam methane reforming, which is the current way today, then we can make lots of CO2. But if we use renewables and electricity, we can make that almost zero. Another potential benefit, not nearly as of high an interest as reducing CO2, but hydrogen requires less air compared to other fossil fuels. And that means if a customer is limited on their capacity, they may be able to increase that just by switching fuels. Next slide. And as you heard, one of the potential negatives of using hydrogen is more NOx. It has a higher adiabatic flame temperature, and therefore that higher temperature generates more thermal NOx. The good news is there's no prompt NOx, but in general, in most industrial applications, the prompt NOx is a relatively small portion of the overall NOx. Next slide, please. And of course, safety, we just mentioned that. Not only does it have a higher propensity to leak, but it also has increased risk of flashback. Next slide, please. So in conclusion, hydrogen has the potential to eliminate CO2, and soot emissions. Next. It is different than most other fuels, so that needs to be taken into account. Next. So we do recommend thoroughly analyzing processes before making the switch. And you're going to hear more about this later, but ammonia might be a good intermediate because it's much easier to carry hydrogen than hydrogen as a gas itself. And to answer the question at the very beginning, is hydrogen an important future fuel? I would say probably, maybe even definitely. Thank you.
Thank you, Chuck. Now we switch to the next speaker, Fouad Said from FIPPR. Please.
Hi, everybody. It's a pleasure to be here in front of you today. So my name is Fouad Said. I'm the Technical and Innovation Director of Fifth Pillar Company. So Fifth Pillar Company is a market leader in burners and combustion system, mainly for mineral industry and boilers industry. So we have celebrated 2 years ago our 100 years old. We have over 100 patents recognized as the best combustion technologies, especially for NOx reduction. The company is based in Marseille, France, with 4 international subsidiaries: Germany, Spain, India, and China. We have also 31 sales offices all over the world. In terms of R&D, we have our own facilities based in Italy, our 5th European Combustion Center, with 30 megawatts installed test furnaces. So I'm working as an industrial combustion expert for 17 years. I'm a working member of International Flame Research Foundation, member of the French committee, and I'm also working member of the task force TEFTAI, Techno-Economic Issues, for the United Nations Economic Commission, especially for the European Commission. So today, I will talk about cement industry. As you probably know, the cement industry is one of the biggest polluters in the world, with around 8% of the total CO2 released in the atmosphere. So you can imagine that the cement companies try to figure out this problem and proposed solutions. The first one to reduce the CO2 footprint in the cement industry is to have a good burner. Good burner design means optimizing and reducing the specific consumption. Of course, how much energy needed to provide 1 ton of clinker. So this is the basis. On the top of that, we are also proposing smart burner technology, smart sensors, which are located on the burners and connected to gateways and DCS in order to monitor all the burner parameters for a better adjustment. Another common way to reduce the CO2 footprint in the cement industry is the usage of what we call alternative solid fuels, ASF. Could be plastics, shredded tires, fabrics, and so on. And there are 2 ways to valorize this ASF: combustion or gasification. Of course, hydrogen. How can we talk about decarbonization without talking about hydrogen? Everybody is talking about hydrogen. This is the case also in the cement industry. But the main challenge is more the availability of the hydrogen. Just to give an example, if we are talking about a 200 megawatt burner, which is quite common in the cement industry, we are talking about 6 tons per day of hydrogen to be fired. Another way to reduce the CO2 footprint is the oxy-combustion, to improve the carbon capture by concentrating the CO2 in the flue gas. And I will have a special focus just after. The clay calcination is also something under study. So the idea is to try to substitute a part of the clinker, which is needed for the cement production, by a synthetic pozzolan, which is produced by a clay calcination process. And the clay calcination process presents the advantage not to release any CO2 in the atmosphere compared to the limestone decarbonation process. And finally, there is also some direct separation process in the precalciner. So this is a pure mechanical separation process. On one hand, we have the CO2 released in the precalciner from the limestone decarbonation, which is completely separated from the CO2 produced by the combustion inside the kiln. So I wanted today to have a special focus on the oxy-combustion in the cement industry, which is combined with firing alternative solid fuel, because this is one of the most promising technology under study. But of course, there are some technological locks. The first one concerns the alternative solid fuel modelization, because when we are talking about solid particles, this is hard to have a good idea of the size, the shape, 2D shape, 3D shape, the density. There is no universal models for the CFD computing. We need to take into account the different phases, so drying phases, devolatilization phases, the combustion of the volatiles, the combustion of the solid fractions, the particle swelling, the radiation, and of course, the ash management. So we are trying to build some solid models in order to be able to modelize any type of alternative solid fuels. The second technological lock concerned the chemical reactions inside the kiln, because of course when we are talking about oxy-combustion, we are talking about high temperature level, 2,500, 2,800 degrees C, and we need for sure to have a CO2 flue gas recirculation in order to master the kiln temperature level. But when we have a very high CO2 concentration inside the kiln, this brings to specific chemical reaction which could degrade the clinker quality. So if you guys want to help the cement industry to reduce the CO2 footprint in the future, these are two topics you can work on. Thank you very much.
Thank you for Fouad, and thank you for saving some time. So now the floor is yours.
Okay. Thank you very much for making opportunity to make a presentation here. My name is Fujimori, come from IHI Corporation. IHI Corporation is one of the Japanese heavy industries. And we supply some power generation systems such as boiler and gas turbines and internal combustion engines. And also we supply production ammonia, such as ammonia production power plant also, chemical plant. So today's I'd like to introduce current status and the challenge for ammonia power generations. And this is general my conclusion, and maybe the solution for energy transformation depends on the local conditions, and such as energy resources, renewable, and economical and geographical situations. For now, I come from Japan. Japan is a very, how to say, isolated by geographically and also geopolitically. It's very difficult to connect the wire or pipelines to neighbor countries. So that case is we need energy. Also, the hydrogen should transport by ships. So in that case, ammonia could be one of the solutions. And also another point is how to realize this process. And we need, I think in the short term, very smart and smooth transition process is necessary, which does not create confusion in society. And the long term, of course, sustainable systems. And ammonia is categorized hydrogen-based family fuels, and so everything comes from hydrogens. And ammonia is combined with, of course, as you know, with nitrogen in air. And also the other pathway is, bottom line is synthesis with CO2. CO2 is captured by exhaust gas or duct or so on. And for ammonia, now the right-hand side is utilization of ammonia. One of the main paths is power generations. And also, ammonia could be used for industry heating. And also, now it's a very hot topic is maritime for ship engine fuels. So today's our companies actually involve all processes, but today's I'd like to talk about power generation. This is ammonia's value chains, and as previous speaker said, ammonia hydrogen is basically the many colors hydrogens existing. I just say blue and green ammonias, and now blue ammonia is a very, how do you say, promising for mass production. but it's necessary to CO2 captures. And also the ammonia carrier and the storage, as you shown, already it's existed. Because already it's an international trading product for fertilizing or chemical feedstocks. And the issue is how to use the energy transformation. That is a technological challenge for ammonia to establish ammonia value chains. Yesterday's sessions, one question arose, and how much hydrogen go from Australia to Japan. I just estimate, and if the hydrogen is 100, maybe in Japan it's about 65 to 70. So it's if you use a best practice way, it's a kind of answer to the questions. And today I'd like to introduce two power generation. One is coal firing with coal combustions. And already this project is going to semi-commercial stage. And this picture shows JERA's power station, 1,000 megawatt power station, coal firing power stations. And the reason why we choose start with coal combustion is low risk, technological low risk, and also low cost for and easy implementation and very speedy. So that's why we started from this position. But this is how do you say the beginning. So. To establish ammonia supply hubs. In the future, of course, increasing coal-firing rate or maybe ammonia solo combustion boilers will be considered. And technologically, at present, we achieve 20% coal-firing. NOx emission level is same or less than coal combustion. Itself. So it is not necessary to any change for gas treatment systems. And also heat transfer is a very minor effect, maybe 2 or 3% changing. So it can be accumulated by boiler design, present boiler designs. So we started from this one. And but however, 25% coal-firing achieve 500,000 ton ammonia consumption and also 1 million CO2 ton reduction per year. So it is 20%, but still it's very big enough to establish ammonia supply chains. So I think now that we work very hard with JERA, and commissioning will be started 2024. And the next one is ammonia co-firing with gas turbine. And in the future, more efficient gas turbine system, power generation system necessary. So we are also seeking to develop combustion technology for gas turbines. Now we choose spray ammonia combustion systems. The reason why we choose this system is in the future, maybe the summer plant is, how do you say, work with renewable energies and also meet some demand. So quick response and flexible operation is critical for these type of, especially for middle class or smaller class gas turbines. So this case, we choose this system. And also the technically very simple, just only push up the pumps and no need for vaporizer, no need for reforming or cracking systems. So it's very difficult to operate for changing load and speedily. And so this graph shows what we achieve right now is we achieve 2 megawatt small gas turbines with 100 pure combustion achieved. Two lines show. The middle graph shows N2O emissions. In the previous model, combustor is actually the pure ammonia combustion generate N2O. And right-hand graph is CO2 emissions reduction rate. As you see, N2O is a very strong green gas effect. So actually, the pure ammonia combustion, the CO2 greenhouse gas emission reduction is decreased. But new combustor will achieve a very satisfactory performance and almost no N2O emissions. So at this stage, very spray ammonia combustion system is very promising, we think. But still, we are looking for a further development for reducing NOx emissions. And this graph shows a challenge for realizing ammonia technologies. And first one is supply chain. This is cost is most important issues. And combustion is flame stability is very critical, and also the NOx emissions. This is a kind of a trade-off relation. So combustion technology should meet two very difficult tasks. So that is what ammonia's combustion challenge. And also, especially for gas turbines, pressurized gas turbines are very promising technology in the future. So the chemical kinetics in the high pressure for ammonia is very, very important. So we need very accurate models also. And also materials, nitrogen, and also heat transfer is something critical. Okay. This is a cost, but I skip. Okay, this is my last slide, and we are now the entrance of the ammonia's world. So many things will be happened in the future. So we will work, everybody's who interested in this technology. Thank you for your cooperation.
Thank you very much. So now we have time. We have a little bit less than 20 minutes for questions. And just as a reminder, after the coffee break, there is also an extra time for question in room 10 in the first floor with the two panels. So do we have any question from the audience? Or is everything clear? Now you see exactly how the industry is going to reduce CO2 emissions. Yes, there's a question. Maybe it's better to use the central mic, sorry.
Thank you all for your comments. My name is Gus Nathan. I'm University of Adelaide, but also lead a heavy industry low carbon research centre and chair a forum on high temperature, low NOx for high temperature processing industry. So we work a lot in these areas. My question is on the cement pathway. We're working on the challenges you mentioned, but I have a question as to whether you have specific data for the oxy-fuel case, because obviously when you burn oxy-fuel, you increase the partial pressure of CO2, which raises flame temperature and also, as you mentioned, can adversely impact on the calcination process. But in addition to that, you have to reroute the heat recovery process to allow, because usually the hot combustion, the secondary air goes directly into the combustor, but obviously you have to reroute that. So do you have any data on the impact of the oxy-fuel, your estimated impact on impact of change into oxy-fuel on net fuel efficiency?
I think, Fouad, this is a question for you about the impact of...
Very sorry, but the sound...
Oh, the sound is all good. So what I understood, correct me if I am wrong, is about the impact of using oxy-combustion in the kiln for the cement industry with the, and recirculating gases. What impact does it have? Is this the idea of the question?
Because you have to, the heat recovery process, usually the hot combustion air from the clinker cooler goes directly into the kiln, but you have to reroute that if you're going to put oxy-fuel into that process. So there's an impact on the heat recovery process within the cement plant, and also you increase the partial pressure of CO2 in the combustion gases, which raises the flame temperature and also has an adverse impact on the calcination. So given that, I'm wondering if you have any actual data, what you estimate the impact on the kiln efficiency is.
Okay, so it doesn't work. Okay, I just want to be sure to understand the question, because I'm sorry the sound is not so good. So you are talking about the efficiency inside the kiln by using the oxy-combustion?
The whole process, because you also have the kiln and also you have the cyclones for heat recovery. And so changing to oxy-fuel, you have to reconfigure the heat recovery process of the plant.
Because the idea of the oxy-combustion in the cement kiln is really to concentrate the CO2 in at the precalciner outlets in order after to liquefy and compress the CO2. But the problem is that by recirculating the CO2 inside the kiln, we have a high concentration of CO2. And this high concentration of CO2 combined with the carbon in the fuel content, in the coal or in the alternative solid fuel, brings to specific reactions, which are endothermic reactions. So we are pumping energy to the process. And in order to compensate this loss of energy inside the kiln, we are trying to bring oxy-fuel to re-increase the temperature of the process.
Yeah, I understand, but I'm saying the data on performance, what the measurements of the impact on the performance. Do you have data on that?
I think it's better that we talk after together, because the sound is very hard. I'm sorry.
No problem, thank you.
Sorry.
I'm Ken Brzezinski from the University of Illinois at Chicago, and routinely I do high pressure chemical kinetics of hydrocarbons. The last speaker, Dr. Fujimori, mentioned the need for high pressure chemical kinetics for ammonia. I'd like to find out a bit more of what you're looking for, what kind of pressure range, and what specifically is not available right now about the chemical kinetics of ammonia, and that would be useful for you.
Thank you for your question. For gas turbines, it's approximately operating pressure is from 20 bar to 50 bar. So it's kind of a range, but as you know, the spray combustion, ammonia is a latent heat will reduce in the higher pressures. So it's more good to operate in the higher pressure. So, and also what important for chemical kinetics is maybe the NOx reduction in the reducing zone, and we need very accurate models. Maybe at present all this mechanism is correct, but we need a quantitatively accurate model. That is very important for designing combustors. This is my question.
Thank you. We have time for a few more questions. Yes?
Hello, I'm Fabiola, PhD student from France. And I would like you to discuss a bit about blue hydrogen, because I don't understand really well the interest of it, knowing that we have to capture carbon in the process, in the SMR process, and changing the fuel in the sequence of the process. So you have to adapt your process, changing the hydrogen, and also capture hydrogen. Why not only capture carbon directly in the process? I don't know if you understand my question.
Yes, if I can summarize.
Yes,
you
please.
are asking why are we using blue hydrogen, because it's very complicated. We have to create hydrogen from methane and to capture the CO2. Yes. So maybe I can give at the beginning of an answer. Maybe, I don't know, Claude or maybe Chuck want to comment that after that. But my first comment will be that is the actual situation is that the majority, I think 90% of hydrogen or 95 is produced this way. So we are not saying that this is a good solution. We are just observing that actual situation and that it needs to change. So I don't know, Claude or Chuck, I don't know who want to react.
Maybe Chuck can add complementary information. It depends, I think, the availability of the hydrogen or the fuels, capacity of capture, and the use or the transportation of the CO2. If you have a mutual transportation, you can involve CO2 storage and CO2 capture and storage. But if you have insulated a plant, it's better to provide directly with another solution. It depends if you have an isolated plant or in an industrial area. Maybe Chuck, you can add information. Chuck, you are here? No.
I don't know if Chuck is still online. Maybe not.
No. Okay.
I'm online. Can you hear me?
Yes,
yes,
please.
Okay. So I agree with what you both said. It's not the ideal solution, but it is an intermediate solution. As has been said, the problem right now is getting enough hydrogen by renewable means. So until we're there, we have to use what's available. So I think long term, we wouldn't be talking about blue hydrogen, but in the short term, that's the best solution in the short term.
Thank you.
Does it answer your question?
Yes.
Oh, thank you.
Thank you.
We have other question? Yes, please.
Hi, I'm Wyatt Culler, Honeywell Thermal Solutions. I have a question with the emissions from hydrogen. So water vapor is also a greenhouse gas. I mean, probably to a lesser extent than everything else. Do you know if anyone's been looking at the impact of transitioning to having a lot more water vapor in the air, and if that ends up still being a net benefit, or if we're basically setting up for another issue we'll have to solve later?
I am not aware of that. It's not really my area. I don't know if one of the panelists have some idea on that. I think there is already plenty of water vapor in the atmosphere, so I don't think it changed a lot, but I'm not expert in this area. And I'm afraid of us.
My understanding that water is not considered a greenhouse gas because it doesn't stay in the atmosphere for very long. It stays in the atmosphere only for a matter of days, as opposed to CO2 and methane and things that can be hundreds of years. So yes, it is a greenhouse gas technically, but it's not considered to be because of the water cycle.
And Sébastien, can I just add to that?
Yes, of course, please.
Yeah. Hydrogen, especially the product of the combustion, water, at high altitude, if aircraft use hydrogen, it is quite important to look at. Because hydrogen, if it's used by aircrafts producing water at high altitude, will act as a greenhouse gas in a very large quantity, and therefore will have an impact, and that's under investigation by researchers. Where hydrogen becomes important, at least in the test that we did, the impact of the water on the walls of the furnace and how that impacts the heat transfer to the load was an interesting challenge, and I think again that part needs further investigation.
Thank you.
Thank you. Yes?
Yeah, hello. This is Mani Sarati from Taust, Saudi Arabia. So my question is related to oxy-combustion in cement plants. And I've been investigating this technology from a techno-economic perspective. And I wonder, when you do your analysis, the cost of oxygen can be rather significant. And the cost of an air separation unit to provide oxygen for an oxy-combustion process, then the post-liquefaction of CO2 can lead to significant additional cost for CO2 abatement. So my question is, in your analysis and maybe in your European projects, what is the CO2 abatement cost, oxy-combustion versus other technologies? And second is, once you have the CO2, you have to store it if you really want it to be a decarbonized solution, and that's an added cost.
Okay. Yeah, thank you for the question. So, of course, you're right. In order to have this technology available on the market, we need to have some economics perspective. We are here just talking about technology to be tested in industrial field and to have a technical proof of concept, because this is the first step. We know that in the coming decades, a lot of technology will be tested, and we don't know which one will be chosen at the end of the day. And this technology will be chosen because of, economics reasons. So now today, of course, it depends on the price of the CO2. It depends on the price of the clinker ton. And this global equation must be done in order to see if it's worse or not. But once again, the first step is to be sure that, technically speaking, we are able to make oxy-combustion in cement plant.
Thank you.
We have time for 2 more questions.
Hi, Garrett Cole, Colorado State University. Wondering if we could get some discussion on the round-trip efficiency of using hydrogen for energy storage purposes. It can be optimistically still lower than 50%. We could get some discussion maybe on the impact of that on global electricity demand, looking at what the potential global demand would be for hydrogen, as we've talked about it for a lot of different industrial uses.
You want to? Toshiro, do you want to comment on?
I'm sorry, I did not hear.
Sorry, I can get a little closer here. So the round-trip efficiency for hydrogen as energy storage can be lower than 50%, even when we're speaking optimistically. And we're speaking a lot of green hydrogen for uses all throughout industry. Could have a significant impact on the global electricity demand. I was wondering if anyone's looking at the interconnection there between the electricity markets and then potential hydrogen markets in the future.
Maybe it's can you show my last slide?
Yes,
and,
of course.
This is if you this graph is IEA estimation, and it is not direct to answer to your question, but ammonia for production, green line is based on the green hydrogen, and the blue and the gray is natural gas-based ammonia production. So
Yes, more or less.
hydrogen production
it's better.
is very depends on the electricity cost, and so if you consider the green hydrogen, the critical point is $20 to $30 per megawatt hour. So that is a very cheap electricity necessary. So conventionally, it's almost impossible. Only the Australia, Saudi Arabia, Chile, or somewhere, maybe the United States, big gigawatt solar could be achieved this level.
Thank you.
I'm sorry, we are running out of time, but we have time just for the last question. Yes, please.
Okay, I'm Stephen Lucas. I'm also from Colorado State, and I believe that one of you mentioned that your company is also, among your combustor systems, you also work with glass companies.
Yes.
I know that natural gas is, glass production produces, well not produces, uses a very great deal of natural gas, but the furnaces, they're in the short term, they're semi-disposable because of erosion, both in the glass, but also from the gas combustion itself and the effect that has on the refractory. Have there been attempts to try to design new furnaces to use hydrogen and the subsequent high temperatures and the possible refractory effects that could have?
Maybe Mohamed will comment more on this, but I can start to answer. Yes, there have been work on that, either to use hydrogen, but also to electrify part of the furnace. But as you know, glass furnace run for tens of years, so you cannot just stop the furnace and make some tries. So it's quite complicated to make a large-scale experiment to see if everything will go well with changing drastically the fuel. So we are working on this, but it's, yes. And Mohamed, I don't know if you have extra comment with glass future, for example?
Thank you, Sébastien. Yes, I think I mentioned that really if you try to retrofit existing glass furnace with hydrogen firing burners, at this moment there are challenges that you have to take into account before a significant investment, and that includes structure and materials of the walls in order to maximize the heat transfer to the load, as well as, of course, linking it with the electrification. So, at least based on the experience we had, it is not a straightforward switch over, fuel switching from hydrogen, from natural gas to hydrogen. It does need some research.
Well, thank you all for your presentation and for the answer and question. And we will wait you on the room 10 after the coffee break. Thank you very much.